Good morning, everyone. We'll start in just another few minutes. For today, there is the live YouTube stream that's running and will hopefully be higher quality. You should also all already have copies of the slides that were uploaded. And in the slides, you can find that there are links to all the code we're going to be looking at today. So if you're having trouble reading the code during the live Zoom, click on the program and download it and follow along as I talk through it, and that should hopefully help. Also, you might have heard that in the last lecture a lot of loud noises. My laptop fan is kind of dying. Post in the chat if you can still hear it, and I'll do my best to stand away from the laptop noise.
If I were a rich man, all day long I'd biddy bum. If I were a wealthy man, wouldn't have to work hard.
Hello, everyone. Lovely to see you all, or as much as we can. And it's a beautiful sunny day here in Melbourne. I hope that after lecture today, you'll maybe go out and enjoy the sunshine a little, take a bit of a walk around, and of course, take your algorithms book with you, because hopefully most of you are carrying it everywhere out of joy and love for this subject. As I mentioned a few minutes ago, if you can't see the code particularly well as a result of Zoom bandwidth issues, firstly, there is a YouTube live stream which is available for the period during the live lecture, which is as about a 10-second delay, but should still be good enough for the experience and even for some live interaction. You can also download the code samples that I'm going to be going through. Every time a piece of code is shown, there is a link to it that's in the slides. If you look at the name of the piece of code and click it, that'll take you to a website where you can download all the code snippets. A couple of class administrative things. In terms of, I had a question about learning outcomes and just wanted to give you a little taste of what you needed to know so far. all we've really covered at this point is the purpose of algorithms and what an algorithm is, and then the start of a basic introduction to the C programming language that includes basic C types, what are their limitations and their uses, and now we're starting to get into control structures. So as long as you're following those key things, as long as you understand the different types in C and where they're going to be limited, you know what an algorithm is, and you're starting to follow along with if-else statements, you are doing fine. I know this class can be a... oh, there we go. Thanks for letting me know that the recording on Zoom wasn't going yet. So in terms of the speed of the class, this class is much like drinking from a fire hose. We're trying to give you a new skill from scratch, which means we actually do have to cover quite a lot of material in a relatively short period of time. However, as long as you go at your own pace working through all the exercises and making sure you watch all the lectures and doing the grok activities we give you, you'll be fine. We're also here to support you as the class goes along. Consultation hours are on today. I'm more than happy to sit with you and help you work through things, and I hope you've all been impressed by how quickly I've been getting to those Piazza questions. And with that, we are ready to get back into some of the material. A quick recap on where we were. Last lecture, we went through a bunch of the different operators, and I'm going to go back over one of the operators, which I realized we could get a bit of a better look at. And we looked at if-else structures. We saw how different code blocks work, how if you use a semicolon, you might run into trouble. But if you use curly brackets, you can very clearly and easily segment your code. And we also mentioned that C was white space insensitive. So it didn't matter how you formatted, how you laid out your code, as long as you had the characters right. That's not to say that laying out your code poorly is a good choice, merely that the compiler will let you do it. And that's a big theme of the course. The C compiler will let you do all kinds of things, and becoming a good C programmer is about recognizing where the compiler's discretion can be abused, where it should be abused, and where you should really stick to the straight and narrow. And the answer to that is most of the time. Let's revisit the modulo operator. We didn't quite cover this as clearly as I would have liked to, so going back to our clock example is probably the best way to think about it. The clock that's presented here is a clock mod 12. You'll see I've replaced the 12 with a 0. This means that if we go past 11, we go back to 0 again. The modulo operator, which is the percentage sign, works on this kind of clock arithmetic. So if you do 11 plus 2 mod 12, you're going to get 1. That's one way of thinking about the modulus operator, is it's essentially telling the computer to do this clock kind of arithmetic. We could also do this kind of arithmetic mod 4. So example, if I do 2 by 2 mod 4, or 4 mod 4, that's going to take me back to 0. And remember, in C, the operator that we use, instead of the word mod, it would be the percentage sign, or the modulus operator. In C, the modulus operator, so x mod n, where the percentage sign is the modulus operator, equals r. And that's going to follow the following condition. This is another way of thinking about it instead of the clock arithmetic, that r is going to be equal to x minus nk, where n is the number we're dividing by, and k is the number of times it fits in. And so r is also the remainder. You can either think about it as working in this kind of modular clock system, or as the remainder left over after division. We also looked at a switch trap at the end of our last lecture, and I'm going to revisit the first one, and the second one we'll also see that follows a slightly different format. Okay, now we are going to live code. I pray that our stream is going to hold up today and that we'll have things in high enough resolution. I actually have an iPad out on the side that's also connected to the Zoom stream to check that you can all see this, but hopefully we're good. Okay, and we're back in it. We have our files all ready for today, and let's remind ourselves what switch 1 was. Switch 1 was this bit of code here. That isn't laid out super nicely because My window needs to be a little bit bigger. Okay. That looks slightly better. And make it a little bit taller. This was giving us a way to determine how long a month was. It was switching based on which month of the year. So with January, we're hoping for 31 days, going to our default condition down the bottom. And after that, we're done. If the month is February, case 2, the length of the month should be 28, plus a day if it's a leap year. And then we have our funny little leap year condition in here. If the case is April, June, or November, that would be case 4, 6, 9, and 11. The length of the month is 30. And remember what this break statement does. This break statement makes sure that we don't keep running to the next case over, which would be the default case. If we removed the break here, while the length of the month would be set to 30 initially, the code would keep going down, and it would run this little line, length of month equals 31. And so our code wouldn't work, and April, June, and November would all be recorded as having 31 days. This brings us to our next example. Switch2 C. This one is pretty confusing, so don't worry if you don't follow it the first time. I'm going to try and go over it a little slowly, and then you can watch it back again if you're having trouble following. In this instance, the break statement is missing in a few places. We have on the outer side of the code, we have a for loop. We're going to get to loops shortly, but this is just going to run through all the different values of I so we can see what the program does for different values of I, starting at 1 and ending at 10. When I is 1, we're at case 1. So x plus equals 4. Add 4 to 1, that gives us 5. But there's no break statement here. And because there's no break statement, we keep going. We don't actually check again if we're in a new case because we've already matched case 1. So we just keep following the lines on this side. So it's been 1, and now it's 5, and now it's 7, and now we hit a break. Okay, cool. Now let's try it with 2. 2 is none of these cases, and so we go to the default. 2 plus 8 is 10. What about 3? The default again. What about 4? Okay, in case 4, we go down and we hit this line over here. So 4 plus 2 is 6. Oh, I missed the 3 over here. The 3 plus 3 plus 8. Trixie, that is why you probably shouldn't write code like this, is because you'll have trouble reading it, especially if you're making the break statements. A much better way to structure this would be to use a series of if statements that make it a little clearer. There are places where you might actually want to use a switch statement, but the moral of the story here is be very careful or you'll end up doing what I just did. Now let's give it a run and see what comes out. There we go. 1 is 7, 2 is 10, 3 is 14, unlike what I had the first time round, 4 is 6, etc., etc. You can go through yourselves and run through this example with the rest of the numbers to see how it works. But that is why switches are both useful and dangerous. Now we get to a different kind of operator, and this one is a little funky in comparison to some of them. This is called casting. In casting, the idea is that we want to convert one variable type into another variable type explicitly. C is statically typed, which means variables can't change their type. So when you have an integer that's A, it's always going to be an integer. However, you can cast it and use it as if it were a float. This means if you add an integer that's been cast to a float, and you add it and you divide it by another integer, you won't end up with the weird integer division happening. Because you've cast the integer to a floating point number, this C compiler and the C programming language will treat it as if it were a float, and so when you divide it by another number, it'll then treat the other number as a float, and overall you'll get floating point division. This is one way to explicitly tell the compiler what kind of types you want to use. Another thing you can also do is if you have an integer and you really do want to convert it to a float, you can't convert the original variable, but you can create a new variable and set it equal to a casted version of the old variable. And I'll show you how to do this in a minute. It'll be easier once you see it live in action. Explicit casting is different from implicit casting in that we use an operator to tell the compiler that we're going to make the cast happen. Typecasting, as I said, is not going to change the underlying type, but it is going to allow the computer to temporarily treat it like a different type. So what does the operator look like? Well, to cast a variable, you put in parentheses the desired type before the name. And you don't do that in a declaration, so not when you say int a semicolon. You do that when you're using it. So another way of saying that explicitly might be b equals, in parentheses, float a. And we'll do a live coding example so that you can see this in a more concrete fashion. There we go. Okay, so here I have two integers, L and M, a float M2, and an integer M3. The first thing I want to point out is how I've declared integer M3. Integer M3 has been set equal to a casted version of M2, which is a float. This is our first example of casting. M2, which was equal to 2.0, is going to be converted by the C compiler into an integer, and then that result is going to be stored in M3. And here I have following a bunch of examples on the different ways that you can do casting. So the first way is there's no casting at all happening. We're doing integer division. So let me make sure that I've run the necessary code to set this up. And we'll scroll back down to our example, and we will give it a run. So printf L on M, that just gives us 1. It's 3 divided by 2, integer division, 1. In our next example, I've done L on M, but that's in parentheses, so that gets evaluated first. And then the answer, the result of that, gets converted to a float. So what do we expect to see? L on M is 1, and now we're casting it to a float, so we get 1.0. In the third example, float L is actually going to be run before the division because of the precedence of the casting operator above the division operator. Float L will happen, and the computer will now treat 3 as a floating point number. So, when we have a floating point number divided by an integer, C will make a further cast implicitly and will convert M to a floating point number for division as well. Therefore, if we've converted L into a float and converted M into a float and do division, we'll get floating point division and 1.5. We could do the same thing if we converted M instead of L. In this following example, we now have L the integer divided by M the float. This is where implicit typecasting happens, just as in the previous examples where the other variables, say L in this one, was implicitly converted. Here, L will be implicitly converted again. The implicit conversion of L is going to turn our 3 into a 3.0, divided by M2, which is 2.0, we get 1.5 again. And the last thing I'm doing here is just printing M3, which was the integer version of M2. The integer version of M2 is going to be 2 again. Here's another pro tip for the long list of pro tips that I'm sure you've already been acquiring throughout this course. Main should always return an integer status. That means the return value of main should tell the computer or tell the shell whether main has completed correctly or not. For a program to complete correctly, the return value is traditionally 0, where non-zero values are specified as particular types of errors depending on what your program does. Why would we bother returning a value from a program? As we'll see shortly, you can chain programs together, and your shell can also tell what the return value from the overall program was. So though you might be writing your one little program for your one specific purpose, this is a way of letting the operating system and users of your program know whether your program completed successfully or not, and if you specify in the manual that you hopefully write alongside your programs what the different error values mean, that will help other developers and other users of your program to figure out what's going wrong. Oh. So, what have we got now? Something new and exciting. At this point, we're ready to start discovering loops. This is the loop syntax in C. 4 with parentheses and then 3 statements, which we'll go over in more detail shortly. One called initialization, one called guard, and one called post. And the other type of loop we have is a while loop, and this only has the guard. And inside both of these, we're going to do stuff. What kind of stuff, you ask? Well, that depends on why you're looping. There are all kinds of reasons why one would want to loop. Hopefully at this point in your computer science careers or in your adventure, you've already seen a few of the reasons why we might want to do this. But the key point is really that loops allow iteration. They allow us to go through things systematically without duplicating code and writing explicitly each time what we want to do. They'll allow us to go through different parts of a string through each character. They'll allow us to go through a shopping catalog that we've stored in the computer. They will allow us to go through days of the week when we've stored the weather on each day inside an array. And so they're going to prove to be a very powerful tool for us in this course, and for life in general. This is the structure of a for loop. And many thanks to Farhana, who taught this course last year, for this slide. The numbers in brownish tell you the order in which statements of parts of the for loop are executed. When the for loop begins, the very first thing that happens is the initialization statement. Remember, there were 3 statements that you put inside the parentheses: an initialization statement and then a semicolon, a condition and then a semicolon, and an updating statement and then a semicolon. Or a condition is another word of another way of saying guard, because the guard is guarding the loop from ending, just like the condition is the condition on which the loop ends. And I wanted you to see both of those 2 words. So the first step, the initialization statement is run. Whatever code you've put in there will be run before the loop begins. Then the condition is checked for the very first time. Is the condition true? If the condition is true, the loop keeps going. That means the body of the loop executes. The statements to be executed all run, and then we go back to the condition, and then we go back to, we run the loop, then we update the value, we update according to whatever is in the update clause. Remember that third part of the loop statement, and then we go back again and we repeat the process. We check the condition, and if it's false, we're done, and we go to outside of the loop, and if not, we keep going and repeat this process. Continuing our theme, I want to introduce two keywords that are also going to be useful for you in constructing loops. The first of these is the continue statement. The continue statement allows you to skip part of a loop. It automatically tells the program, don't do whatever comes next in the rest of the body of the loop, just go right back up to the update statement and keep going along. Let me see if I have a code. Yes, I do have a code example for us to see this shortly. The other important statement is break. Break tells the loop to terminate right where it is and not keep looping. This is used slightly differently from the switch statement break, but in both cases, it tells you to stop what you're doing and exit the control structure. So if you, in this statement here, if I equals 2, break, don't finish doing the rest of the loop. And let's see those in action. What I have here, my first loop is just basic print the numbers from 0 to 10. Let's give that a run. Oh, our loop has empty body. Oh, I forgot. I put a semicolon here. Oops. This means my loop had an empty body, but it still ran. And I think I was actually not initialized because I set this up improperly. There we go. The loop still runs. However, the loop body is empty, which means every time the loop goes around, it's just going to increment I. So remember, our loop structure is initialize, check the guard, run the statement, but it's a blank statement because there's a semicolon, update I, check the guard, run the blank statement, update I, check the guard, blank statement, and when that's done, it comes to another code block. Just because you have your curly braces does not necessarily mean that it's connected to the previous control structure. You can have a code block that is not tied to any code structure at all. So after our loop runs, at the end of the day, I is going to be 10, and then we print F, and we print 10, and that's it. Our next example just shows you the continue statement. It's going to be a little less tricksy. Go from 0 to 10, update each time. I don't have a semicolon here anymore, so this should work. But if I equals 3, continue. So let's see what we get. 0, 1, 2, 4, 5, 6, 7, 8, 9. So continue has made the loop skip whatever comes next. Our example of the break statement, and this is also a nice time for us to see a while loop. A while loop is very similar to a for loop, just grossly simplified. All that happens is the while loop checks the guard, runs the code, checks the guard, runs the code, checks the guard, until the guard is false. You'll notice here that I'm still incrementing I, because if I didn't increment I, the loop would never progress. I would just stay the same, and the same exact code would be run over and over and over again until the heat death of the universe. Or probably until the computer failed. That might come a little earlier, I think. Anyway, let's give this one a run. 0, 1, 2, 3, 4. This at I equals 5. This statement has become true. So we do a break, get me out of here, and the loop terminates. And we're ready to move on. With every loop, there should be an invariant. What is an invariant? It's something formal that you can say about a variable or about some data structure that you have that never changes. What formal property is the same every time the loop runs? This is generally going to be the thing that we have in our guard, but there might also be other things that you can say about the program, even if it's not explicitly encoded in the guard, that holds true every time your loop runs. For example, if you are sorting, as we'll see a little bit later in this class, here's your tiny preview. If we're sorting a list one by one, you might say that the leftmost item is always going to, after we've run the loop once, the leftmost item is always going to be smaller than one more along. Because if we're sorting as we go, you want to make sure that every time the loop runs, the leftmost element the element that you're looking at on the left is not less than the one before it. Muddled that up in saying it a little, but you get the idea. Invariants should always be satisfied by the initialization. Why? If you don't start the loop with your invariant being true, you're not going to be able to prove that thing consistently as you go along. Your guard is going to fail and your loop is not going to work. So that can be something to check when you're building your loops, is that your initialization is correctly establishing the invariant. On every iteration you go through, you also have to make sure that something changes. In the while loop, if I had I is less than 10, but I never changes, the loop's just going to keep running. And then eventually, when the guard is false, you want to plan your loop so that the outcome you're desiring has been achieved. One thing we're going to see soon is how you can use these three kinds of statements very powerfully to do mathematical proofs, which prove statements about your program. And this is going to expose a very deep connection between the nature of mathematics and the nature of computation and the nature of computational proofs. So, another one for the pro tip basket. Try and start your loops at 0. This will make your code a little easier. Of course, this isn't always going to hold true, but in general, this is a nice way to begin. Now we've got a whole bunch of program demos. You've got all these useful tools. You've got if, else, you've got your types, you've got your loops. It's just about time for us to see what we can do. How can we put it together? This is where things start getting a little more sophisticated. Don't worry if you don't get every program the first time round. Go back, watch the lectures, write it out by hand, and see what it takes. Ooh, it's a long list of programs. I have written out for the day what all of the programs do, just to remind myself, and we're going to go through them one by one, and this will probably take us through the end of the week, depending on the speed at which we go. Okay, let me switch back to the terminal. Again, if you're having trouble reading the code, click the link on the slide and you'll be able to access these programs and follow along. The first one on the list is daynumber.c. Enter a date in day, day, month, month, year, year format. Okay, let's do the 1st of January 2021. The 1st of January is the first day in 2021. Unsurprising. Let's try the 30th of January just to make sure our program is working. Yep, all good. What about the 1st of February? You get the idea. How does this program work? Well, let's pull up the code. Here is the code. It's using a whole bunch of the building blocks that we've seen so far. We have a block where we initialize some variables, we print a statement, and we read in a couple of things at once. So this is the first little part that I want to point out to you. Our format string is starting to get a little more sophisticated. We want 3 integers, and each integer should be separated by a /. And then we're going to put the result of these integers into these 4 variables. This is inside an if statement, checking that we've read in 3 things, that scanf has produced a return value of 3. If it hasn't returned a value of 3, we know something is wrong. Printf invalid input, and then run this function called exit with a hash-defined value called exit failure. The exit function is located within standard lib.h. This is the standard library for C and has a whole bunch of super useful functions that almost every single program will use. And it's also defined, it has a hash defined in it for exit failure. Moving on. We have a case for, we have a variable that tells us how many days February has. We have use of the modulo operator here to check if we're in a leap year or not, and whether to add that extra day. Remember that conditional statements are evaluated to either 1 or 0, and because this is a logical statement, if it's true, it's going to be equal to 1, and so when we add that to 28, we will get 29 days, thus a leap year. So this is a fancy way of showing off how you can use a conditional as an integer and not just as a true or false value. We start off with saying that the day number is at least how many days into the month you are. So if it's the 13th day of the month, we know we're at least 13 days in. Then, for every month, starting with the first month, up until the month that we're currently in, do the following. And then when you're done with doing the following, move on to the next month. So what is the following? Well, if the month that we're currently looking at is February, add to the number of days in February. If we're in April, June, or November, add the number of days in April, June, or November. Otherwise, we're in the other case, and add 31 days. So imagine I've asked for the 1st of March. Day num will be set to 1, because I'm asking for the first day of March. And then this loop is going to start with January. It goes through and adds 31 days, because there are 31 days in January. It then will update the month variable, will be in month number 2. And it will add the length of February, which might be 28 or 29 days. The month will be incremented one more time to 3. 3 is not less than 3, and so the loop terminates. And at this point, every time, day num has had more days added to it. It's had the number of days of the current month, plus the full number of days in every other month. The program then prints it out using another format string. It says, leave 2 characters for this, 2 characters for that, and 4 characters for the year. And then print out the integer daynum, which is the day number in the year. And for each argument, it's going to correspond to the first argument to printf corresponds to the first format specifier in the printf, the second to the second, the third to the third, etc., etc. And return 0, our program has been successful at that point. So that's our first one. Now we have some examples of for loops. Here's a very basic example. I'm not going to spend too much time on this one because you have already seen it. Okay, let me switch to a different directory where I have some more of the examples. There we go. For loop 1. Oh, looks like I didn't even include for loop 1. For loop 2 is just going to be this basic iteration through I and j, where I is going to be run n times, and j is going to be run each time up to the value of I. Which means if I is 0, there's no number that's less than 0 that starting from 0, so j won't be run at all. If I equals 1, 0 is less than 1, so 0 will be run. If I is 2, both 0 and 1 are less than 1, so j will take on both of those values, and we're going to get a little chart output of for loop 2. A little chart that outputs for each value of I, which values of j are possible, given the condition that j must be less than I at all times. So that's going to be one of our loop invariants. We have two invariants here. The first one is I is less than n times, which was 5. And our second loop invariant is that j is always less than I. Given these two things, you can figure out mathematically what is the full set of values that are going to appear. Not super exciting, but necessary. Our next program is not much more sophisticated than this, but we're starting to ramp up. Let's take a look at the output first for loop 3. This is giving us 3 squared, and then 3 times 10 squared, and then 3 times 100 squared, etc., and printing us just a nice kind of looking visual. Why the weird numbers at the end? We've covered this in earlier lectures. We're starting to run into problems with big numbers that exceed the size of the integer type. You can solve this problem by using variables that have room for more, such as a long. A long is a bigger size of an integer, but that's going back to our lectures on types, and we're not going to rehash too much of it now. What does this one look like? Pretty simple. It says leave up to 8 spaces for the first thing we print, times up to 8 spaces for the next thing we print, but left align it this time so that we get that nice looking triangle thing, and then leave 12 spaces for the answer. What are we printing? We're printing the value of I, then we are printing the value of I again on the other side of the x, which we're using as the time symbol, and then we're printing I by I, which is the same thing as I squared. Each time this loop runs, I is starting at 3, and then each time the loop runs, we're going to multiply that by 10. So this is one of the key features of this particular program that you should be looking at. Instead of doing I plus equals 1, which is a really common pattern for for loops, we're saying each time multiply the current value of I by 10. And make that the new value of I. So I starts at 3, 3 becomes 30, 30 becomes 300, 300 becomes 3000, etc. Okay, actually this one, let's display the output first as well. What does this program do? This program calculates something actually useful. And this is where you're going to start getting programs that actually solve problems that you're really having in C. I realize many of you are used to doing this in Python, but knowing how to do it in C is quite powerful and quite important. Not only because C is used in a lot of places, but because C is really fast. So as our computations start involving larger and larger numbers, C is going to become an excellent tool for you to solve your problems. This program calculates how much money you would have if every month you're saving $100 and you are getting a particular interest rate as measured by the chart, say 2, 3, 4, 5, 6, or 7%, and the interest is compounded monthly. Now, I realize that, like you, I've been binging on avocado toast, and so our parents' generation tells us we'll never be able to afford houses, but with monthly savings of $100 and an interest rate of 7%, you could have a full $10,000 towards your house price or your avocado toast slices, whichever of those things you apparently are deciding between. So let's see how this program works and deal with the problem of our parents' generation later. Whole bunch of hash defines. This program is going to start getting complicated, but follow along with me and we'll make it through. First thing, how big do we want our chart to be? We want to show 7 years. We're going to say that each month we are saving $100. The minimum interest rate we care about is 2%, and the maximum interest rate we care about is 7%. Now, I realize that interest rates are even below 2% at the moment, but stick with me. We're thinking of like a positive future where we can actually save something. So we're setting up some basic variables here. What is the month? What is the rate? And what year are we up to? What is our balance? And what is the monthly rate at which we are contributing? Notice that these variables are going to be used inside the loop because things will change. They're no longer going to be constants. However, we will use the constants in order to initialize things. This prints the start of the table. We have our heading line. What are the monthly savings with monthly compounded interest? And then we have the table heading. One of the really important things to look at in this program is going to be how to do alignment, how to make sure that the table lines up just right. So both the maths and the format specifiers are going to be pretty important to understanding how this one works. This is the first part of the header construction that worries about alignment. And you can see here that we have the percentage sign for D to indicate that we want 4 spaces. And then we have this weird double percentage sign. Why a double percentage sign? If we were to put 1 percentage sign in our format specifier, in our format string, C would treat this as a format specifier and would expect us to be printing a variable. But if you look at the program output, we're actually trying to print a percentage sign. So what the double percentage sign is it's escaping the format string, the format specifier, to allow us to actually print a percentage sign. So double percentage sign in a format string will print an actual percentage sign. Okay, good. We've got the header down. Now we have to do the rows of the table, each row by row. So let's look again. And maybe, if I'm being fancy, I can have that on one side and the code on one side. I don't think this is actually going to work. Not enough space on the screen. Okay, let's just look at it row by row, and we can always print out the output from the program again if we want to see it. Starting in year 1, up to the maximum number of years that we specified in our hash define. So starting in year 1, up to year 7. And every time the loop runs, go up 1 year. The first thing we do, we print after 1 character space wide, because we're just going from 1 to 7. After years, and now we have another for loop. Why do we have another for loop? Because we're actually going to have to do the compounding on a monthly basis. And because we're compounding on a monthly basis, we're going to iterate through each month of that year and figure out what would happen. So at the lowest, actually incorrect. Excuse me for a second, the loop here is the loop that controls the various different rates. So remember, we were looking at this for 2% interest, for 3% interest, etc., etc. This over here is the monthly loop. So in the outermost loop, we're producing the results for each different interest rate. For that interest rate, set the starting balance to 0. Calculate the as a decimal the percentage monthly rate, given that the rate in the hash define was the annual rate, so maximum annual percentage rate, so we have to convert that into a monthly rate. And of course, the interest rate gives you funds above your existing amount. It's like an added percent. So you take 100% of what you had plus the monthly interest rate is going to be how we factor in the monthly increase. So for each month in the year that we're looking at, go through each month, multiply the existing balance by the amount that of interest it should have accrued plus the rate to account for the fact that you're gaining money on top of your existing money, so this monthly rate here, and then add to it the amount of additional cash that you're contributing each month. So if you're saving another $100 every month, that should also go into the balance. And when you have looped through all the months, print the balance for that rate for that year. When you finish going through the months, go to the next rate. And when you've done all the rates, go to the next year. And when you've done all the years, you're finished. And you can print a new line, and that's the end of the program. Return 0, program was successful. So to just show you once more what it looks like, monthly saving of $100 compounded monthly with different annual rates. After 7 years at 7% interest, you end up with a wonderful $10,000. We have time for one more example for today, and then we'll go through our last few examples tomorrow and potentially even start getting to functions because we're making excellent time. As I said, if you feel things are going a little too quickly, feel free to drop me a line with questions. And also, I have a little quiz on Piazza where you can put in topics that you'd like me to review more if we end up having extra time. So with that, let's look at our last program for today. This one is day number dash squash. Let's see if I have it already pre-compiled for us. Let's run it. Okay, we've seen this before. Day 94 for the year. Okay, great. What does this program look like? Why is this different? Oh my God. Who is the awful coder who wrote this? What we see here is a program that's perfectly valid. I'll compile it for you. Clang number squash.c. No warnings, nothing. Compiler is perfectly fine. But this is still bad code. Why is it bad code? Because even though it conforms to the C specification, it can be processed effectively by the compiler and produce correct output, it is unreadable. Stylistic and readable code is very important. Firstly, because in the future your colleagues might have to read the code. You may leave your position. You may no longer be around. And your code someone will probably have to come and update or maintain your code. So that's reason number one. Seems fair enough. Reason number two is in some ways a little more obvious and in some ways a little more subtle. You will have to read your code. And if you don't know what your code is doing because you've written it like this, it will be not only very hard to debug, but when you come back to it after a while and you say, oh, I wrote this program a year ago that performs this very useful piece of functionality, you won't be able to figure out what you were thinking at the time you wrote the code. And so the last message from today is, although you can get away with all kinds of funky stuff in C, perhaps you shouldn't. And I'll see you all tomorrow, an afternoon class so you can sleep in, or spend the whole morning working on your wonderful Foundations of Algorithms grok exercises, and I will take any more questions now. Thanks, everyone. Xuaneng, was that a question about workshop? There are workshops this week.
Oh, okay. Thanks.
If you already missed yours for this week, you can probably go into another workshop, or there's also a recording online if you did have to miss it. Although doing it live is really the way to go, because then you'll get actual help with your problems.
Yeah. Thanks.
No worries. Any more questions from today?
Hi, Professor. This is one thing. So I just get a little bit confused about the leap year. So how do you find, like, when it's a leap year, like as 28 plus something, and there's lots of conditions, and how do you make sure that it's 28 plus 1?
I'm having a little hard time hearing you. Could you possibly repeat the question?
Yeah. So there's one question about like the length of the year.
Oh, yeah.
Yeah. So in February, how do you make sure like one code the writing length of the year equals 28 plus like y divided by 4, and then some like 3 conditions?
Okay, yeah, I can go through that a little more slowly for you in a second. Let me pull that program up again.
So like I just don't think that. So how do you make sure like it's 28 plus 1? Like for leap year, there are 29 days in February, and like how do you make sure? Because I only see plus and then like
Yeah.
the bracket and the conditions.
Okay, I'll pull it up again so that we can discuss it briefly. Give me a second to switch over. Okay, you seeing it?
Yeah.
And it's this little bit over here.
Yeah.
Okay, so let me actually pull up something slightly different on this computer. And run this little piece of code. So 1 plus 1 is 1 equal to 1 equals 2. 1 plus 1 does not equal to 1, which is a false statement, equals 1. Why? Because if you were to ask what the value of a condition that is true is, say let's say 3 is greater than 2, that's true. Oh, sorry, this is my fancy Python thing, my fancy C thing being confusing. If I print to F normally, you can see that 3 is bigger than 2 is actually equal to 1. Because it's true, true is equal to 1, and false is equal to 0. Therefore, in my program over here, if this thing in parentheses, it's a logical statement. So if the logical statement is true, that whole thing becomes equal to 1. If it's false, that whole thing becomes equal to 0. Because of this weird fact of C, we know if we can make the condition be true whenever there's a leap year, that statement will become 1 and we'll get 28 plus 1. If we're not in a leap year, the statement will be false, and because false is equal to 0, that'll be 28 plus 0. Does that help clarify a bit?
Yeah, I got it. Thank you so much.
Great, no worries. Any other questions before we're done for today? Okay, I will see you all later. Thank you very much, everyone.